Okay. So, as I mentioned, you can get away with this problem without doing an integral. Okay? What you can simply do, you can simply say, oh, okay, every charge is same distance, so I will just go ahead and kq over x squared plus a squared. Okay? But then I have to account for cosine theta, which is x over square root of x squared plus a squared. That also works. You see, I didn't use an integral. But it's risky. Okay? You have to know what you are doing if you are going to do this. Yes?
If we don't have the ring perpendicular to distance,
Okay.
we wouldn't do that.
No. Ring perpendicular to distance, not being a ring, for example, it could be ellipse, could be any kinds of perturbation to this problem, would break this symmetry, so we wouldn't have this easy way of getting away from this. Okay? For example, what about a disk? If you have a disk, so here's the question. How do you find the electric field due to a disk? It's not tilted, it's like this. So for disk, you have basically something like this. This is the central point, and perpendicular to that central point, we have another point. And let's call, now I can use this. In my notes, I have used A for this, so let me use A for this time. And let me call this R. We are not confused, right? Now, I have plus Q again. So, are all charges the same distance to this point? No. Some of them are closer, some of them are further away, right? But we can still use our ring analogy. We can still use our rings solution in this problem. So we imagine that if you just take a ring out of this, so let me just duplicate this, make it a bit smaller like this. If I take a section like this, let me call this R, and this tiny bit over here is dr. Do you understand the geometry? So in that ring, in that tiny ring, we can say that again, every dq that is there is still the same distance. So let me plot a dq over here. And this distance is r squared plus a squared square root. So far, did you miss anything? No. So I have a formula for the whole thing. Like if I call this whole thing dq, let me just call this whole thing over here. dq. You see what I had as q here as a ring is now dq of a disk, because disk is made up of tiny bits of rings. That's how I'm thinking about it, right? And then I can just simply use this formula above to figure out the tiny bit of electric field dE because of this dq, and it's going to be k times dq times, that's where you are going to get confused maybe, but In the previous problem, this was x. So in this problem, it's going to be a, right? So this x is a, right? And this a is r, and this x is a again. Sorry, I switched to my old notes, so I don't want to get confused, so I prefer you to get confused, I guess. Are you confused? Not at all. Brilliant. Now, if I integrate this, can I still take out everything except dq? Yeah, like, I mean, can I do the following? Can I just take this, duplicate it, just take the integral over here and dq over here? Can I do this? No. Why? dq is related with r. Does everyone get it? Maybe not.
I don't understand how dq is related with
R. How dq is related with r? So, what was your name? Rifat. Fatih, sorry. Fatih is claiming that dq and r are related. So, why is that? Because if you have a larger ring, you will have more charge. Of course, obviously, we need to say again that this q is uniformly distributed. All right? So since dq is uniformly distributed, it's not like when you buy XX large, you pay more. There's no such thing. But when you buy a longer ring, larger ring, you pay more, right? So the ring is this ring. So if its radius is increased, assuming that it's the same thing, you have more charge inside it. Actually, it's proportional to the ring's area, right? So let me give you another definition. Surface. So we have already seen linear charge density. Now surface charge density. Surface charge density is usually shown by this sigma. Very hard to draw it properly. Okay, now I'm happy. And it will be q over pi r squared. Do you agree with this? Q is the total charge, pi r squared is the area of the disk. Yes? Now, how dq is related to r? dq is related to r by this. dq is equal to sigma times dA. And what is dA? 2 pi r dr. Very good. dA is the area of this ring, and it's 2 pi r dr. Now, there are at least two ways of thinking about it. One way is the area over here, you can think of it like this. I have r and then r plus dr, right? So the area in between is pi r plus dr squared minus pi r squared. That's one way of thinking about it. And you are going to get pi r squared plus 2 pi r dr plus pi dr squared minus pi r squared. Right? This will take care of this. And, okay, where's dr? And you can see that this is way smaller than 2 pi r dr. So dA is equal to 2 pi r dr. Did you get it? Another way of thinking about it is the following. This is a ribbon, right? Do you know what a ribbon is? Ribbon, like this. Sherit. Okay, a ribbon that is formed into a ring. So you can think of the length of the ribbon times the thickness of the ribbon. So the length of the ribbon is 2 pi r, and the thickness is dr. That's another way of thinking about the area of that ring. In any case, dA is 2 pi r dr. And what is sigma? It's q over pi r squared times 2 pi r dr. How do you study this stuff? You, let's say, watch the video one more time, and you have a blank of paper. You try to reproduce it from beginning to the end, and whenever you're stuck, you go watch that part again, and then you start from blank again, just like studying piano or guitar, whatever. Do it and you will get it. Don't worry. Looks complicated, I accept, because first imagine the ring, then imagine the area, then imagine the integrals. I mean, you can easily get confused in one of those steps, right? Good. So we got rid of PHYS here. We have dq is equal to q 2q r dr over r squared. So we have a relationship between dq and r. That's why we now can take this and put it back in here. Take this, put it back in here. Right? Let's do that. dE is equal to integral k times a over a squared plus r squared 3 over 2 2q r dr over r squared. Right? Believe it or not, it's actually not a hard integral. dE is equal to, let me take ka over r squared out and suspiciously leave 2r dr over a squared plus r squared 3 over 2 inside. I left 2r dr inside because, yes, do you have a question? Yes, very good. So now you can see that my problem is now condensed into this integral problem. How do you solve that integral? Substitution, very good. So you just say u is equal to a squared plus r squared. Then du is 2r dr. Do I need to explain this? No? And then you have integral of du over u to the power of 3 over 2. Right? Then you can think of it as integral of u over minus 3 over 2 du. Then you can just write minus 3 over 2 plus 1 minus 3 over 2 plus 1. Did you follow all this? What do I get from this? Minus 1 over 2, 1 over root u. Is this correct? No, it's not correct. It's minus 2, right? So, no problem at all. So minus 2 over square root u, which is minus 2 over a squared plus r squared square root. Any questions at this point? No questions. Yes.
Can you open the ring example, the first one?
Yes, of course.
before this? You said it's not related to x here, but isn't it related to a? Because it's the radius.
Y-
For the integral, like we took out.
very good question. Very good
I
question.
think A should have stayed inside. Because we did it in this case.
Yes, excellent point. So here's the thing. Here, in the first ring question, A is not changing. A is also constant. It's just a ring of radius A.
But how do you understand this constant?
You understand it because, for example, if it was an ellipse, then A would change, right? As you go around. This is longer A, this is shorter A. But you have a circle. So for circle, A is always the same. Everywhere around. Like you look at the charge distribution and you look at how it is positioned. They are all positioned at the same distance A. But in the disk, if you choose a certain R, they are positioned around R, but that R can be small, large. It is a variable of the problem. Thank you very much. Okay. E is KQA over R squared minus 2 over A squared plus R squared to be evaluated at where? Where do we go? 0 to R. Does everyone agree with this? So I start with 0 and I grow until the big R, right? So I go from 0 to R. Okay, so my electric field is 2kqa over R squared times 2 over A minus 2 over, okay, I sent 2 out, so it's 1 over A minus 1 over A squared plus R squared, square root. Everybody agrees with this? Do you have any objections? Any objections, any comments, ideas? No? Does the units check, Efe? You think yes? Very good. So one other way of writing this down is E equals to 2kq over R squared and taking A in, and I get maybe a prettier formula. Good, very good. Now let's do the following. Let me also write it down. Yes.
How can we check the units in this equation?
Very good question. So this is 1. This is length per length, so everything is fine. This is k times length, k times charge divided by length squared. So now I want to ask you, oops. Yeah. Yes, tell me.
For this, why don't we use double integral?
Why don't we use double integral? Very good question. So maybe since it's an area,
Yeah.
right? We are actually using double integral. How? We took the first integral when we did the ring. We are taking the second integral when we are doing the disk. But if you want to take something like this, like x, I don't know, like x dx, something like this, and it will be very, very hard. It would work with if it was a square. Then you take the double integral, okay? But we did also take the double integral here. You just respect the symmetry of the problem, okay, and take the double integral accordingly. To answer you more technically, we did take the double integral. Just our coordinate system was cylindrical, okay? So we took this 2 pi dr d theta integral, okay? Good. Now the question is, what happens if my r is much larger than my a? So imagine this r being huge. What happens to my formula? Well, I need to do some, yes.
Can I answer?
Yes, you can answer it.
It becomes the electric field due to the point charge. If R is 2, no, sorry. A is 2.
So actually it doesn't. So let's see what happens. But thank you for contributing a thought. So sigma is q over pi r squared, right? Do you remember this? So we have q over r squared here. Let's just sigmify it. I don't know. Like q over r squared is sigma times pi, right? Do you agree so far? Now what is k? K is 1 over 4 pi epsilon 0 sigma pi 1 minus a over square root a squared plus r squared. So these pi's go away, and I'm left with this beautiful formula. Let me just use technology. Okay. This is how it looks like for the electric field. And when I'm looking for electric field when R is much larger than A, then what do I get?
It's plane.
Hmm?
It's like plane.
It is like plane, and it's constant. That's also true. And I just simply get sigma over 2 epsilon 0. Do you see it?
R is infinite?
R is infinite. R is going to, okay. R is much larger than A means, yes, R is infinite. Now you are going to ask me why you didn't deal with it like this, because R was downstairs, and if I take R to infinity, it would go to 0. But it's not 0 because Q is also going to infinity, and they are going at the same speed, right? So Q and R squared are actually related with each other over sigma, which is a constant. They are both going to infinity. That's why I first got rid of both of them and put instead that constant. And then I could take R to infinity and get 0. So R to infinity, this one goes to 0.
Or A can be small.
Or A can be small, in which case it's again 0. Yes, that's also true. A going to 0 is also making it 0. Very good point. Everybody is on the same page here. This is very, very intriguing result. It is telling you that if you have an infinite sheet of charge, so it goes on to infinity, okay? Let me just write plus plus. Then no matter where you are, over here the electric field is sigma over 2 epsilon 0. Over here the electric field is 2 over sigma over 2 epsilon 0. Over here it's sigma over 2 epsilon 0. So it doesn't depend on the distance. If you have an infinite plane of charge. Does it make sense? Okay. It's a property of infinity. But for a physicist, when something is 10 times larger than the other thing, it's infinitely larger than the other thing. So we are going to use it for capacitors, for example. We are going to have a capacitor with a distance, right? We are going to just assume that they are so large with respect to this A that we can use this formula. Do you see what I mean? Very, very good. Tell me.
I couldn't imagine why it becomes a plane, why it becomes
Oh.
then it becomes line.
Very good. So you are saying that wasn't it a disk? How did you turn it into a square? Is that the question?
Yes.
Yes.
Makes plane, but I think that it should be a line.
It should be a line,
Yeah. Line.
aligned. So you want something like this.
Hocam line doğru.
Türkçe söyle.
Doğru hocam.
Yok, yani bütün tamamını Türkçe söyle.
Yani plane yerine ben doğru. Yani ben doğru olacağını düşünüyorum.
Ah, okay. So, but you see, this is a disk. This is a disk. And I'm taking R to infinity. So it's going bigger and bigger and bigger and bigger. So it's going to...
Ama altı zero olmuyor mu? Altı sıfır olmuyor.
No, I mean, we talked about like either make A 0 or make R infinity. Let's make A this, but R is going to infinity. Yes.
You could also think like this table is the plane of sheet, and there is a proton that is so close to the sheet.
Yes, yes.
So it feels like it is an infinite.
Exactly,
large.
exactly. If there is an ant that is an ant distance to this plane, it would see this as infinite, right? Something like that. So far, so good? Very good. Let me talk about this electric field due to charge sheets a bit further. For example, if I have a charged sheet here, and let's say it's plus sigma, okay, then what is the electric field over here? You already know this. Please tell me.
What was the question?
Okay. Is it not clear? It's infinite. Goes to infinity. What is it? Sigma over 2 epsilon 0, right? Sigma over 2 epsilon 0. Is it clear?
Yeah, I couldn't catch what is the red thing. Oh, red.
Yes.
What is the red house?
How about over here?
Same thing.
Same thing, but pointing on the other direction, right? In the opposite direction. So if I have an infinite sheet, over here the electric field is in this direction, everywhere the same. Over here, everywhere the same. Yes? Let me do another example. So this example is separated from this example. Another example. This time I have infinite sheet. Goes to infinity, goes to infinity. okay, but it is minus sigma. Then what is the electric field over here? It is pointing in this direction and it's sigma over 2 epsilon 0. And over here it is pointing in this direction and it's sigma over 2 epsilon 0. Yes?
Can we say that one plane like this is creating uniform electric field in whole universe?
Yes. Yes, because one plane like this is actually cutting the whole universe into two. Right? It's infinite in principle. Yes.
May I ask something? Is there a difference if the infinite plane is a circle or square?
It doesn't, because infinite plane is
It's just infinite.
just infinite. It can't be circle or a square, right?
Yeah, we can show.
It doesn't have edges,
Yeah.
right? Yes, yes. We are on the same page, don't worry. Any other questions? Now let's bring these two examples together. Let's say I have an infinite plane of plus sigma here and infinite plane of minus sigma here. Do you understand this? Yes? So what is the electric field at this point, and at this point? Do you understand the question? Very good. Typical exam question, by the way. Okay. So, yes.
I can answer.
Yes, yes, of course.
In the middle, sigma over epsilon 0, in the left side and the right side, directly 0.
Very, very good. So, let me just write it down like this. What was your name? Sorry? Umut is telling us that over here it would be sigma over epsilon 0, over here it would be 0, over here it would be 0. Okay? Quite counterintuitive, because how can it be 0 over here when it has negative charge here? Or how can it be 0 here when it's positive charges here and it's closer, right? But that's the beauty of this infinity. They have infinite range of effect. So basically what's going to happen is that everywhere here you would have sigma over 2 epsilon 0, sigma over 2 epsilon 0, and everywhere here you have sigma over 2 epsilon 0 pointing to the left. But because of the other one, everywhere here it's sigma over 2 epsilon 0 to the right, over here to the left. Are you following? Over here also to the right, pointing towards the negative charge. So if you sum them up, you get 0 here. Sum them up, you get sigma over 2, not 2 epsilon 0, sigma over epsilon 0, and sum these up and you get 0. Are you happy? Yes? Yes.
Can we explain parallel plates?
Yes, yes, exactly. That's how we explain the capacitors, right? So in the capacitors, we are going to come to capacitors. We are going to use this formula. There is this A, right? And there is this plus Q, minus Q, and let's say the distance D. We are going to say that these kinds of parallel plates, assuming that the distance is much less than, let's say, this distance L, okay? Assuming that it's a tiny bit versus the huge area, we are going to say that electric field outside is 0, but electric field inside is sigma over epsilon 0, which is Q over A times epsilon 0. Okay? Alrighty. Any questions, comments, ideas, suggestions? Anything at all? No? I know you are bored. It's just a physical thing right now. But we have 13 more minutes of torture. I'm having fun, but I understand that it's because there are so many new things that you are learning. Yes. Unutmuş olabilirim. Bu birincisi. Bu ikincisi. Çok sağ olun. Would you object if I put these lectures to YouTube, to my channel? You won't object? Are you sure? If you find something inappropriate in the videos, just let me know and I will edit it out. Like, hocam, you asked my name and I answered the wrong question. Something like that.
Hocam, the
Yes.
notes you upload in the
Yes.
sites
Yes.
you gave us is the same with the notes you wrote right now.
No, but I will also include those notes. Okay. All right. Despite the physical condition that you are in, I'm going to solve the hardest question involving integral. Okay? So that you will know there is nothing harder than this. Okay? And you will see that it's doable. It's not impossible. So, and the hardest question, it's hard because of the integral, nothing else. It's just a line of charge. We already solved the horizontal charge and at this point, and the integral was easier. This time the integral is harder, that's all. So I have plus q uniformly distributed. The length is L. All right? What is the electric field over here? So let me just choose dq over here. Choose x over here and dx. Are you confused in any way why I did these choices? Well, first of all, why do we need integral? Because, as you can see, every charge has a different distance to the middle, right? But we still have some sort of symmetry here. And the symmetry is the one that we already discussed. So we have, let me use the arrow.
That is the total length, right?
What?
L is the total length.
L is the total length, so let me fix that. Did I fix it or did I make it worse? Okay. DE. Now, as you can imagine, there will be always another dq over here that would have another dE in that direction, right? And its x component would reinforce the other one, but the y components would cancel, right? We don't have this symmetry if it's not right halfway over there. Like, I can actually make it less confusing if I say that this distance is L over 2 and this distance is, I'm always stumbling upon this dx here, so let me take it somewhere else. All right? L over 2. L over 2, L over 2, and that's dx. This thing is dx. Now, dEy's will cancel each other out, right? So since they cancel each other out, we are only going to deal with dEx. And what is dEx? It's basically dE times cosine theta, where theta is this one. So far, so good? Yes? So what is dE? dE is k dq over a squared plus x squared. Right? Can I change this x to y? I'm very, very sorry. Because it's y, right? Y, I was writing x anyways. All right? So I'm wondering what's going to be dEx, which is k dq over a squared plus y squared times cosine theta. We have a lot of trouble here because we have q, which is variable, theta, which is variable, y, which is variable as well. So nothing comes out from the integral. Everything needs to be defined in the same terms, okay? And you only know what to do here by experience, okay? You have to have been solved, if that's an English tense, I don't know. You have to have been solved this question in past so that you know what to do. And that's what we are doing right now, all right? We are solving it for the first time. You go and practice it 1 time, 2 times, 3 times. You will be good to go. And what's going to happen is we are going to use theta and not y, okay? Let me show you how it works out. So, do you agree that y is equal to a times tangent theta? Do you agree with that? Because y over a is tangent theta, right? Now, what is dy? Yes?
A times secant squared theta dt.
Very good. A times secant squared theta times d theta. How do you know this? Or how can we get this? Tangent theta is sine theta over cosine theta, and f over g prime is f prime g minus g prime f over g squared, right? So you get 1 over cosine squared theta from this. Okay, just trust me. A over cosine squared theta d theta. Now we have a connection between y and theta and dy and d theta. Now let's connect dq with dy and y with q. Are you following? So we had 3 variables, dy, let's call it y, q, and theta. We have connected y to theta, and we are going to connect q to y so that they all are going to be connected to each other.
Why the q is not constant? I imagine that q, the big q,
Yes.
capital Q distributed all the L.
Yes?
So I just think that dq should be constant each part of the.
dq is constant over the whole thing, but it is just proportional to dy. That's the. So let me tell you this way. If you integrate dq starting with y, you are going to get like larger and larger q until you reach q over 2. or let's say you start from minus L over 2 and you integrate all the way to plus L over 2, you get the whole Q. But
So dq is the same, but we add each
yes,
other.
dq is the same, dy is the same,
Yeah.
and there is a constant of proportionality between them, which is linear charge density. So dq is, dq is linear charge density times dy. Do you understand this? 3 minutes to go. Let me do it quicker, and then we will come back and resolve it. Just for finishing. So lambda is q over L. So I have q over L dy like this. And I have an expression for dy here, so I can just write it q over L. I am going fast, so don't blame me. I am aware of it. I will go slower next time again. So I have dEx equals to k times q over L a over cosine square theta times d theta times cosine theta over a squared plus, let me just use this one right away, a squared times tangent square theta. So you see everything turned into theta. And by some magic, we are going to get rid of a lot of those theta. Wait a moment. K, Q, A over L. And A squared comes out, let's say. I have 1 over cosine square theta times cosine theta d theta and 1 plus tangent square theta. What is 1 plus tangent square theta? Yes, 1 over cosine square theta, right? Yes? So this one cancels out this one. We are left with very simple integral, and that's what I was telling you about experience. Just the moment you see this problem by experience, you will realize that everything will go away and it will be only cosine theta d theta. Okay? With practice. So what is left is to take the integral, and you are going to get E is equal to kq over LA times, what is the integral of cosine? Sine theta, to be evaluated at, let's call it minus theta 0 and plus theta 0. By minus and plus theta 0, I mean these ones. This is the minus theta 0. This is the plus theta 0. Do you understand? Yes? So it's going to be 2kq sine theta 0 over LA. And what is sine theta 0? Sine theta 0 is L over 2. L over 2 divided by L over 2 squared plus a squared square root. So just for finishing the question, here it is. L over 2 over L times A times L squared over 4 plus A squared. That was the hardest question ever. Okay? Nothing harder than this.
What's written behind, not behind, on the L square?
4.
4?
4. Kimi almadık? Kökünü almadık. Alalım. Ayıp ettin. Okay, you have some cancellations here. Very good. So take good care. We don't meet tomorrow. Don't forget, okay? Instead, we are going to torture ourselves for 3 hours on Thursday. So please come well fed, well slept, ready to go.